Welcome. This video is to go over Chapter 8. I think we should be able to get everything into one video, so let's go ahead and jump in and start talking about it. So the first thing we're going to talk about is introduction to search algorithms. Now, I do want to let you know that this is definitely just an introduction. There are entire job focuses, entire careers focused around search algorithms and how to make search algorithms faster and better. So just understand that this is definitely just a introduction, but it's enough of an introduction. In fact, most developers only know so much into search algorithms, again, because it's just a specialized field that we know enough to do these things on an average, when we're dealing with normal code. Okay, we want to do a linear search or a binary search. And even more so, I would even say that at times when we're developing, we don't even really put too much thought into what algorithm is going to be used. We often use built-in functions to whatever language we're utilizing at the time. But this is definitely something to know. It's important to kind of understand. It's going to be the same thing when we start talking about the sort algorithms next. Same kind of concept. Again, there are entire career practices that are that surround creating new algorithms for sorting as well. So when we talk about search, we're wanting to locate an item in a list of information. And as we've already said, there are two types of algorithms that we're going to talk about. One's the linear search, and one is the binary search. With the linear search, it's just simple. We're going to start at the element, the first element, and just kind of go through until we find the item. Here's an example. We've got an array of items. And if we want to find the value 11, we're going to start at the beginning, go 17, nope, 23, nope, 5, nope, 11, yes, we found it. So we've gone through 4 elements to find that 11. Now the downside is if we search for something that doesn't exist, then we have to go through the entire array to say that that item doesn't exist. So at worst case, we always have to go through every single item. And that also stands for anytime we want to search and it happens to be the last item. So imagine if we're doing searches on very large arrays, this can get very time consuming, especially if you find that the items you're searching for tend to be more towards the end of the array more commonly. So they could that can definitely make sure that your array and the search algorithm is really slow, depending again on that size of the array. So with that said, this is kind of the algorithm. It talks it through, and all this is saying is if we were to write this as code, we're going to sit in a loop that starts at index 0, and we're going to have some flags. And we're going to look one at a time at each element until we find the right element. Then we're going to turn the flag on and set the position. And then we can fall out of the loop and return that position. Here's an example of code. Again, is exactly what we just talked about, where we've got the pointer to the index of where we're going to be searching. We're going to have a position that will store the position of the found item, and then we'll have a flag that tells us we even found it. So now we're going to sit in this while loop going one at a time looking for it. If we find it, great, we'll set that flag to true and we'll indicate the index, and then later we'll return it when we fall out of that loop. So why linear searches if they're slow? Well, they're easy algorithms to understand, and it's easy for the code to run through. And but again, they are slow. Now, keep in mind when we start talking about slowness, it's all relative, right? If we are talking about an array of size 10, then we're not going to find using linear search to be so slow. In fact, the next algorithm we're going to show you is, for all intents and purposes, faster unless the array is small. And if the array is small, you may find that the next type of search actually is slower because it has to do more work. So what is the right size when you're talking, these trade-offs? Again, that also depends on the hardware that you're running on. That depends on how cluttered the OS's memory is. In my opinion, unless you are really working on extremely large arrays, you'll find that this disadvantage of being inefficient is not as problematic as you'd think. I think if you're getting to array sizes of 1,000, then you might start seeing some disadvantage. But again, we're talking whether you want your code to be milliseconds or can 2 seconds searching through an array. Is that too slow? So it's kind of one of those things that depends on your use case and what you're trying to accomplish and so forth and so on. With the binary search, this one's a little bit more complicated. And what it does is it continually divides up the array as it's searching things. So first, it's going to have an array, and you're going to, let's say we have this array of pieces, and we're going to kind of put these elements here. Beautiful. And what's going to happen at first is it's going to pick out the middle item. Let's just say that for sakes that that's the middle item of the array. And it's going to compare this item, and it's going to say, hey, is this equal to the item that they're searching? No. Okay. Is this item greater than or less than the item that they're searching? And from there, it's able to say, okay, well, this middle item is greater than what they're looking for. So that means that if we're going to find what they're looking for, it's going to be in this part of the array. So when it does that, it now just focuses on this part of the array. And it does the same thing. It says, okay, now go find the middle one. And in this case, let's say that because there's an even items, this one's the middle one. And it's going to say, hey, is this the item? And if it says no, once again, it's going to say, well, is it greater than or less than? And let's say this time it says it's less than. So what we're going to do is now look at to the part of the array that is to the right of the item. And in this case, there's only one more item left. So the middle is the array. And it's going to say, hey, this item, is it equal? No, then the item that we're looking for is not in this array. Or, yeah, that is equal, and that is the item. And that's when we would let you know what the index is of that item. So that's how these binary searches work. It just keeps dividing the array up smaller and smaller until it finally finds the item, or it runs out of array to actually divide up. Like here, when we ran down to finally there was only one element left in the divide up, so either that was going to be our item or not. Now, with that being said, one of the biggest things that you have to remember about that is that it does require that this array be in order. It has to be in order for it to find these items. So kind of take a look at this next one. This is kind of give an example. Again, we're going to be looking for that middle item, which is here. So this is where it's divided up into three. It divides up the array into three items, which is kind of the left, the middle, and the right. And then in this case, the first case here, it's 11. So yay, we found it. And we would return back to that position. But in the next case, searching for 7. So here's the middle. Is this 7? No. Is 7 greater than or less than 11? Well, it's less than. So that means we now need to search and divide this section of the array up into left, middle, and right. And we know that doing that, 3. So is 3 equal to 7? No, it's not. So is 7 greater than or less than? Well, it's greater than. So now we're going to search to the right. We can pick a different color. Well, there's only one element left in this array to the right, and we're going to say, is 5 equal to 7? No, it's not. So we would return back that there is no, that this item was not found, and we would return back a -1, meaning that there is no 7 in this array. So this is an example. This is kind of that pseudocode to let you know what we just did, what we just talked through. I'm going to let you take a look at that. If you have any questions about it, shoot me over something. Again, this is just pseudocode of exactly what we just visually did. And this is actually a program that shows how the binary search would be written out in a program. So again, trade-offs. It is definitely more efficient than that linear search. In fact, we know that the max is comparisons using log 2 to n, and so that's great. Like I said, but what if your array is only 7 elements long? Then again, the binary search may not be faster than the other search. And again, when it comes down to whether speed is important or not, are we talking, does something need to be milliseconds versus a couple of seconds? What's the speed, and what's the trade-off? Do we want to have something that's a little bit more complicated to running in our program versus something a little bit more simple but a little less efficient? There's a lot of trade-offs, and it really does come down to making sure you're using the right thing for the right time. I will tell you, for most of my career, except for one part of my career where I actually was working with a company where we were working with huge arrays. I think I talked about it in one of my previous videos where we were mapping out the United States. We most of the time we just don't really care what is being done in the background. Oftentimes we're going to use stuff that's given to us as part of the base code, and we're not going to care whether it's actually using binary or whether it's using the linear. We won't care unless all of a sudden we find that the application is just not working or going as fast as we need it to. That's when we start to care about things. Otherwise, we just really don't usually. And that's just something to be thoughtful of. Most of the time when we're developing, we just don't get into stuff that's this big. Disadvantages. The big disadvantage, and why oftentimes I typically would use linear over binary, is that you have to have the array sorted. And so, again, okay, well, if we're going to sort the array before we can do a binary search on it, there's a cost right there. We may have to sort that. Now, if it's already, for whatever reason, sorted, great. But if we have to sort it, then that also is an overhead that you have to add into your binary search time. So let's talk about sorting algorithms. Sorting algorithms arranges things into certain orders. We're talking about alphabetic, or we're going to be talking about numeric, either ascending or descending. Again, there are a bunch of different algorithms out there when it comes to sorting. The main two that you'll typically see when working with sort is bubble and selection. Oftentimes, bubble is the most commonly used just because it's quick, it's simple. When it comes to actual sorting, it's not as quick as other sorts. And so when I say quick, I mean that writing the code or utilizing code is pretty quick and simple and not too much to think about. So what happens in a bubble sort is it's going to continue to compare 2 elements at a time, starting with the first element. So it's going to first look at 1 and 2, and then it's going to look at 2 and 3, and then 3 and 4, and 4 and 5, so forth and so on. And what it's going to do is it's going to say, hey, is the second item less than the first item? And if it's, well, again, I should actually say it's going to, if you're looking to do a sort from lowest to highest, then if the second item is lower than the first, it's going to swap the two. And then it's going to do, like I said, that second element and third element, same thing. If the third element now is bigger than the second, is lower than the second element, less than the second element, it swaps them. And it keeps doing this all the way through the array. Then it goes back to the beginning and does it again. And it keeps doing this until it is able to run through the entire array without doing any swaps. That's why it's called the bubble up. And that's because think of what's happening here. Let's say you have an array of 10 elements, and it's the numbers 0 through 10, but 10 is at the very bottom of the array. It would only have to go through that array twice because it would keep bubbling. So when it looks at element 1 and 2, or if you want to be more in line with C++, if it looks at element 0 and 1 and it says, oh, well, 1 is less than 10, so we're going to swap those numbers. Then when it looks at 2 and 3, it's going to say, oh, well, 2 is less than 10, and it's going to swap those numbers. And it's going to keep doing this, slowly bubbling 10 up to the top. And in this example, because that's the only number out of place, it would literally be able to bubble that all the way to the top in one pass through the array. So then it would have to go back to the array again and do another pass, and this time it wouldn't have to swap anything, and that's how it would know that it's done. So take a look, and actually if you want, do a Google search on bubble sort. There's a lot of visuals out there, and like I said, it's one of the most common sorts. In fact, it's funny is I was not too long ago watching a movie, and it was some kind of hacking movie, very fiction kind of thing. But they even put the phrase bubble sort into the dialogue. So it made me laugh because anyone with some basic development skills would recognize the word bubble sort, and it kind of makes it, oh, look, they know what they're talking about, yay. They probably don't, but it was fun and magical. All right, so here's what it kind of looks like. So we got 17, 23, 5, and 11 in this array. Well, compare the values. 17 and 23, it's in correct order, so no exchange. 23 is greater than 17. Now, again, this is saying that we're sorting from least to biggest, right? If we were doing biggest to least, then this would be incorrect and we would swap. But again, for this example, we're going from least to greatest. So 17, 23 are already in the correct range. When we compare 23 and 5, not in the correct order, so these two would swap. So now we have 23 is going to be over here, and 5 is going to be over here. Now with 23 here, it's going to compare. Well, again, 11 is less than 23, so now 23 is going to go here, and 11 is going to go here. So now our array should look like this. (17, 5, 11, and 23). Now, I believe the next slide says that, so let's go to that. And it does. There we go. So now, we're going to compare again. 17 and 5. Oh, nope. So this guy is going to come over here, and 5 is going to come here. So now we've got 5 here, and 17's here versus 11, and we know that 11 is smaller. So now this is going to
playing from MLT10287.
Thank you, my Alexa. So now we have 17 here, and we've got 11.
Sorry, I'm not sure.
We got 11 here, and then it's going to say, hey, is 17 and 23 in the correct order? It is, so leave it alone. So now we have 5, we have 11, we've got 17 and 23. Great. Now we can go ahead and clear that out because we're going to look at the third pass, and we're going to say, hey, is 5 and 11 in the correct order? It is. Is 1117 in the correct order? It is. Is 1723 in the correct order? It is. Great. No exchanges. So this array is now in order. And we'd be done with the bubble up. Here is an example of us actually writing that as a program. Again, I'm not going to spend too much time on it. Have fun taking a look at it. You should take a look at it. And like I said, really do Google bubble sort. It's pretty neat, some of the information you'll find out of it. It's definitely easy to understand and implement. It's definitely a benefit. And its disadvantage is it's definitely slower. Again, because there's so many passes that could happen, as your array gets bigger and bigger, the bubble sort will get slower and slower. And I will tell you, unlike the other piece that we were talking about, the search algorithms, sorting algorithms, it doesn't take too long. Your array doesn't have to get too big before you start to find your bubble sort getting slower and slower. So kind of keep that in mind. If you're looking at sorting 1,000 elements in an array, you're probably going to be a lot slower than you think. You might take a few seconds to sort that, just because it has to make so many passes through the array. In fact, there is an algorithm, a measurement to tell you how the slowest of what the bubble sort could be on the worst kind of sort. But they're not showing it here, so we won't talk too much more about it. On a selection sort, the concept for sorting in ascending order is locate the smallest element in the array, and we're going to exchange that element with position 0. Locate the next smallest element in an array and exchange it with position 1. Continue until all elements are arranged in order. So here's our num list. And again, the system would go and say, essentially, okay, 2 is the lowest, so move it here, and 11 will go here. And then the next will say, okay, 3 is the next lowest. Oops, so let's kind of put 11 here. Take this and move it here, but we're going to put 11 here. So now that's not there anymore. And then it would say, 11's now the next highest, and it's going to grab it, and it's going to move it here while putting 29 here. And that's how that works. So now we got 2, 11, and this is exactly showing this in real time. So that's the first swap. And now, again, this 3 is going to come over here. And then let's see if that shows up in the next slide here. Yep. So now we've got the 3 in the right spot. So now 11 and 29 have to swap. And there you go. And then since 29 is the last element, it knows automatically that it's in the right spot. Now this is sorted. So as you can see, it feels like this went faster because it was able to do this. But again, remember, behind the scenes, it is still having to go through the array. It's reading through the array, which again, reading through an array is a lot faster than continually swapping elements. So that's why, again, in this example, this type of sort is faster with larger array elements. I will tell you, just like the search algorithm, for the most part, you're going to use built-in sorts of the language you're working with, and some are smart to and will say, oh, well, there's so many elements, let's use this kind of sort. Some are smarter than others, and what you're going to find is you're really not going to pay too much attention. You're just going to use the sorts that are just kind of there for you to use until you start to play with your program and you're testing your program. You're going, wow, this is taking way too long to sort this. And then you're going to start caring, and you may actually start digging into, well, what kind of sort is being used behind the scene? Should I use a different type of sort? What kind of sort? And there's quite a number of sort algorithms out there, depending on what kind of sort you're trying to do. So again, the selection sort, the benefit is it's more efficient than the bubble sort for the most part, since fewer exchanges, but the disadvantages may not be as easy as the bubble sort to understand. That doesn't typically in my mind register as a disadvantage, like I said, the disadvantage could be that compared to other sorts, depending on their, like I said, if you get into this, there's a whole career around it, and some people will say, oh well, depending on what the distribution of values are in your array versus what kind of information you're trying to sort, different types of sorts will be faster. So it's just one of those things. Finally, they briefly talk about sorting and searching vectors. And this is because sorting and searching algorithms can be applied to vectors as well as an array. Then you have to slightly modify uh, your usage of the vector to do this, because remember, you need to use that ampersand sign. Otherwise, you're getting copies of the values, not the actual value in the element where you're trying to swap. So no need to indicate vector size. Functions can use size member function to calculate. Again, this is just a short, brief intro to searching on vectors. All right. So that's the end of the slides for this chapter. I know that it was quick. The video is pretty quick. It's going to be more about getting into the homework and utilizing and actually working with some of these algorithms. That's going to be a little more time consuming. Just a note, when you're doing your homework, I need for you to use the algorithms that were presented here and not any built-in methods or functions to sort or search your arrays. And so just keep that in mind. And again, that was chapter 8. Thanks for hanging out with me.